Hello! Welcome to Pre-Calculus again. Today we're going to do section 11.2, which is another thing that you will be doing a lot of in calculus, which is finding, well, area under a curve. Okay? So we're going to be finding some areas. This is the second, probably most biggest thing in calculus that you do. In fact, it's related to the derivative, but you won't really make that connection until next year. All right. So here we go. So finding the area under the curve. Now, as you guys know, curves can be created by a lot of different functions like parabolas and square root functions and x cubed and sine functions. If it was just a straight line, we could figure out the area under a curve easily by using rectangles or other shapes like trapezoids. But finding an area under like a shape like this is going to be much more difficult. And for instance, finding area under a curve is actually essential for doing a lot of statistics. Okay, figuring out, what percentage would go in a certain range on a some type of test of some sort. All right, so basically what we're going to be doing in this lesson is approximating the area under the curve in most scenarios here by using rectangles. Okay, so we're going to divide up the area under a curve into a rectangle, and then of course hopefully you remember you find the area of a rectangle by doing length times width. All right, so the rectangles will just be an estimate, and there are two methods here that we're going to look at. This first method is called the right rectangular approximation method, or RAM for short, and it is useful, but it is of course just an estimate here. All right, so here is a curve, and when we're doing the right rectangular approximation method, we're going to be having the rectangles. Basically, if the curve is going upwards like this, these rectangles are going to be touching the outside of the curve, okay? And we are using the right corners are touching the curve, the right corners of the rectangle. All right, so we're going to take, this is part of x squared function here, all right, and we're looking at the interval from 0 to 3, okay? Even though the function keeps on going, we're only going 0 to 3. And we're going to subdivide this area into 6 intervals, okay? 6 equal width intervals. So we're going to take this 0 to 3, and each interval, because we have a 3 distance from 0 to 3, and we're cutting it into 6 equal subintervals, each interval will have the width of a half, okay? Now notice these rectangles, because we're doing the right rectangle approximation method, are all touching the right corner. The right corner of each rectangle is all touching the curve. So you got points here that you can see, like right there. Okay, another one there. Okay, and so on. All right, so now we just need to figure out the area of these points. All right. So, yep, that's all the stuff I just said. Okay. In this particular method, because the rectangles are sticking outside of the curve, it's going to be an estimate. Now that is dependent on how the curve is shaped, but in this particular curve, the rectangles are sticking out, so it really is an overestimate of the area. So you have too much area. Okay, so then you make a little table, all right, and you're going to have to do something like this on your test. Make a table and show the intervals that you're using, okay, so the intervals should all have the same base. Like I said, that was the width. The base and width, that's the same thing. All right. Now the height is actually determined by the function, okay? And remember what our function was? Our function was f. Ooh, that's a big. Let's try that again. Delete. Smaller. Go smaller. Okay. All right. Sorry about that. F of x equals, this function is x squared. Okay, so we get the height by determining the result of putting the right endpoint of each of the intervals into the function, okay? Now, if this was the left approximation method, which is actually coming up, you would use the left endpoint, okay, and put it into the function, all right? So the height here is going to be a fourth because, okay, remember the function's x squared, so you're doing 1/2 squared, which is equal to a fourth. Okay, then you put 1 in, 1 squared is 1, etc., etc., etc. 3 squared is equal to 9. Area, because we were using rectangles, length times width. 1/2 times the fourth is equal to 1/8, which is 0.125. All right, so to get the sum of the area under the curve, all we do is we sum up all these rectangles. So we're going to be adding them all up here. All right, so add all these up and you're going to get the total area for this particular one. All right, so for the left rectangle approximation method, we're going to actually do the same thing, only the rectangles are going to be touching the left corner of the curve. All right, once again, 6 intervals. And notice you can't even form a rectangle here, okay, on this first interval, because that is equal to 0, okay? And so the rectangle wouldn't exist. F of 0 is equal to 0. That doesn't even exist. You don't even have a rectangle there at that point, because 0 squared is equal to 0. All right? So same dealio here. You're just using the left endpoint touching the curve. It's going to be an underestimate this time because the rectangles are, you see these gaps here? Okay, that's why it's an underestimate, because you have area that is not actually filled in here. All right, so like I said, the first interval, the area is equal to 0. All right, and then because of this, okay, oops, let me get rid of all that purple stuff there. In this particular method, we're using the left endpoint. Okay, the smaller value, and because the curve is going up here. All right, and so we're going to get an underestimate. Okay, so the actual answer is really an average. I mean, it's not an exact answer, I don't believe, but you can get a better answer by averaging the right rectangular approximation method and the LRAM, the left approximation method. All right, so there it is. Here is the average of the right and the left. Add them together, divide by 2. And so a good area approximation is 9 1/8. Okay, 9.125. All right. But there's actually a better way to find area under a curve. And that is with something we call the integral. Okay? And the integral is better when you can't get an exact answer. Okay? So this is the symbol for a definite integral. Okay? It looks like an S because you're summing a bunch of infinitesimally small rectangles. See, the closer those rectangles get together, okay, the smaller those rectangles get. So imagine if instead of using 6 rectangles, we used 600, all right? That means there's less gaps and more precision. So if we use an infinitesimally small size rectangles, like 6 trillion, even more rectangles in that curve, we can get a pretty much exact estimate. All right, and integrals can be definite or indefinite. Okay, definite integrals have a starting and stopping value. Okay, so like if you see this little S symbol and 1 to 3, that means it starts at 1, ends at 3. The dx here at the end is saying that you are figuring out with respect to x. In other words, you're going from 1 to 3 on the x-axis. Okay, start at x equals 1, end at x equals 3. You could integrate with respect to y too and go on the y-axis, but we're only doing x-axis this year. All right, so let's check out a couple examples here. We're going to do the area underneath a line. Okay, that's a slanted line. So we're going to use the area formula for a trapezoid to figure out the area underneath a line. Okay, and so you have 2 bases. You have a height of the trapezoid. The height is actually the x distance, so the height is actually running horizontal instead of vertical, and you'll see what I mean here. In fact, I will be kind and sketch it out for you a little bit. All right, so here is a line. So imagine you have a line here, and you wanted to figure out the area underneath the curve, okay? So if you wanted to go between these two values, all right, and this would be like x1 here, and this would be x2 here. All right, so the height is actually going to be this way, okay? So it's like a trapezoid on its side. Okay, so the height is this way, and then you could say this one's base 1 and this one's base 2. And the base 1 is actually the y value, okay, here. So actually base 1 would be here, and base 2 would be a little bit higher. Okay, and I hope you can see that okay. I'll draw it better on the actual example, which is coming up next. All right, so clear the ink there, go on the next page. Next page. Woo. Okay, all right, having too much fun. All right, let's look at example 1 here. We're figuring out an integral, figuring out the area of the function on the given interval. Okay, so we are going from 1 to 7, x equals 1 to x equals 7. The idea that we're trying to do is figuring out the area between the function's line and these two regions here, okay? And also bounded by the x-axis, okay? So it basically forms a trapezoid, so you can use the trapezoid formula to figure this out. All right, so first off, you need to figure out what is the height of the trapezoid. All right, so what do you guys think the height of the trapezoid is? Height of a trapezoid here is going to be between 7 and 1. Okay, so that, not between 7 and 1, but it's the difference of 7 and 1. So the height of the trapezoid is going to be 6. Like I said earlier, the height is going to be horizontal, okay, because it's like a trapezoid on its side. All right. Base 2 of the trapezoid is the y value right here. You could call that base 1 if you want. All right. And base 1 of the trapezoid is the y value right here at x equals 1, this point right there. Okay, so we need to figure out base 1 and base 2, then you just use the trapezoid formula. All right, base 1 we get by taking 0.5 and we multiply it by what x is, which is 1. So base 1 is just going to be a half, or 0.5. Base 2, likewise, you take the function and you substitute the x value in. All right, so the x value here on this interval is 7. Okay, so we would end up with 3.5 or 3.5. All right, so now we need to figure out the area of this trapezoid, which is the area under the line. So the formula for the area of a trapezoid, as I mess things up here, but is base 1 plus base 2, okay, it's on the previous slide, divided by 2, because you're averaging the bases, you're figuring out the average of the bases. So that's basically like the length there, and then you multiply it by the height, okay, which is, remember the height is the difference between the two endpoints on the interval, okay? So here we're going to have 1/2 plus 3.5. Okay, so that's just 4 divided by 2, and we multiply it by the height. The height is going to be equal to 6. All right, so we have basically 4 divided by 2, which is 2, times 6. So our integral has area of 12 units squared. Remember, area is measured in units squared. All right, got one more example, but we're going to have to put that in the second part. So enjoy the commercial break here.